Hi everybody, welcome to this video on pK concentration equations. In this video, we're going to go over those equations that we use to calculate drug concentrations, predicted drug concentrations. And so this video will build off of the previous video that I've posted where we went over pK constant equations. So go ahead and take a look at that video as well if you haven't. So before we get into the actual equations themselves, I want to go over a really important concept. And so this concept will help you understand how the equations are interrelated between the various dosing frequencies, single dose, multiple dose, steady state, and hopefully demystify these equations just a little bit because they can be quite a bit unpalatable given all the different terms that are contained within the equations. Start with this equation right here, 1 minus e to the negative number of doses times elimination rate constant times tau over 1 minus e to the negative rate elimination constant times tau. And so what this is the multiple dosing factor. So this is what we add to a single dose equation to get multiple doses or even to steady state. And so let's see how we can actually convert between these different frequencies of dosings. So how do we convert between single dose to multiple dose to steady state? Let's start with single dose. So a single dose can take many different forms. It will just depend on which exact dosing scenario we're talking about. In general, it will take this form of d over v times e to the minus ke times t, and this is little t, so that's time. Now let's take a look at how we convert that into a multiple dose. So what we do is multiply that multiple dosing factor to each exponential term found in the single dose equation. Then how do we convert a multiple dosing equation into a steady state? As n number of doses increase, that multiple dosing equation gets converted into the numerator being a 1 and the denominator remaining the same. So I know that might be a little tricky or confusing or not very straightforward. So let's take an example to see what that looks like. So here's the numerator of our equation. Now let's do a couple different scenarios differing the number of doses to see what we come up with. So in this example scenario, I just picked some numbers here. The number of doses is 2. The elimination rate constant is equal to 0.05 hours to the negative 1. And the dosing interval is equal to 8 hours. So what does this look like when we plug it into the numerator of the multiple dosing factor here? That equals 1 minus 0.45. So still an actual number that will have an effect on a drug concentration or is basically not equal to 1, right? So let's vary the dose again. This time let's do 3 doses, keeping the same elimination rate constant and dosing interval. As you can see, this is getting closer to 1 now. We've gone from 1 minus 0.45, so 0.55, to 1 minus 0.3, which is 0.7. Let's again increase the number of doses. Let's say we did 9 doses here. Now you can see that we're getting pretty close to a negligible decrease from 1. 1 minus 0.03, so 0.97. Finally, let's hammer it home here with one more example. As we can see, it becomes very small. The e to the minus ke tau becomes very, very small, so that virtually it is equal now to 1. And that is how we go from a multiple dosing factor into making it a 1 over the 1 minus e to the negative ke tau. So I hope that you can play with this a little bit, see how this multiple dosing factor converts a single dosing equation into multiple doses, which eventually reach steady state. Now, let's take a look at those pK concentration equations in the same format that we did in our pK constant videos. So what I have here is a table set up on different dosing scenarios: a bolus, intermittent infusion, continuous infusion, extravascular, usually oral is what we think of there. And then for each different dosing situation, we have a single dose, a multiple dose, and a steady state dose, with the caveat that the single dose for a continuous infusion really refers to a continuous infusion that was stopped before it reached steady state. So here are some of the concentration equations that we have, almost all of them. And the concentration, should be noted, is usually in some sort of amount over volume. So typically we'll see milligrams per liter, but you might see something else, but it's going to be some sort of amount of drug per unit volume. So here's the first equation. C equals dose over volume times e to the minus KET, little t being time. And which equation does this, or which scenarios does this apply for? That's for a bolus single dose and for an extravascular single dose. The only difference being that you have to add in the bioavailability factor, FD over V. So you put the F in the numerator with the dose for an extravascular dose. Going down to the next equation, what we can see here is now we have the same equation as the first time, but now we have the multiple dosing factor. So which scenarios do you think this applies for? You guessed it right. The multiple dose for bolus and the multiple dose for extravascular. Continuing down, what we see here is that the top is now removed in the multiple dosing. So the 1 over for the multiple dosing, and it becomes just E over the 1 minus E expression. And what scenarios do you think this applies for? And you've probably caught on to the pattern. Yes, this is the the steady state equation because the numerator of the multiple dosing factor becomes 1. So a single steady state, of a bolus dose and a steady state of the extravascular dose. Let's take a look at some other variant equations. Here we have K naught, so that tells us that this is some sort of infusion over elimination rate constant times V times 1 minus E to the KET prime. Remembering that T prime is the infusion time. So what scenarios does this apply for? This applies to the intermittent infusion, single dose, because it's T prime, and it could apply to that situation where a continuous infusion is stopped before reaching steady state. In that equation, we substitute T prime for T because we're just putting the amount of time that that continuous infusion was going for before it was stopped. Continuing on, let's look at the conversion here. As again, we can see the multiple dosing factor is put back in. And the scenarios that this applies for are just continuous or intermittent infusion multi-dose. Finally, the last equation again is going to steady state, so it goes 1 over that expression, and that applies for, you guessed it, steady state and intermittent infusion. And then one final equation we're going to look at is the steady state concentration equation. And this can equal a few different things. It can look like this, and it can look like this. And just like we saw in that pK constant video, this is one of those special equations because it's at steady state that can be used for any route. So, with all that said, what scenarios does this steady state equation for any route apply for? And it applies for any route at steady state. So I hope that understanding how we convert between single dose equations to multiple dose equations to steady state equations and then actually seeing where those equations fall into line helps you understand a little bit more and demystify all those confusing equations that we see when we're calculating doses or concentrations at particular doses. Thank you very much for your time.